Welcome to homework.
So in this problem, we're going to be looking at some soybean-based biodiesel. So for part A, we have this soybean-based biodiesel derivative, C18H33, CO2, and then they write ME. So ME just stands for methyl, which really is just a CH3 group. And so I'm going to write that on the molecule here so that we can see what elements we have. So for part A, we want to write a balanced equation for the complete combustion. So combustion is reacting this with oxygen. And in the process, we're going to form CO2 gas. Actually, I'm going to give myself a little bit more room there. We're going to form CO2 gas, and we're going to form H2O liquid as well. Okay, so let's start by balancing out the carbons. So on the left, we have 18 plus 1 plus 1. That gives us 20. So we'll put a 20 here in front of the CO2. And maybe I'll make that a different color so that we can see that just a little bit better. 20. Okay, now let's balance out the hydrogens. On the left, we have 36. So we'll go ahead and put 18 in front of H2O, give us 36 hydrogens on the right. And let's look at the oxygens. So it looks like we have 40 plus 18, which gives us 58. So we'll go ahead and write 29 in front of the O2 species to give us 58 O2 or oxygens on the left. Okay, so this is the balanced equation for the combustion of this species. For part B, we'll calculate the delta H of combustion. So delta H is just equal to the sum of the delta H of formations of the products minus the sum of the delta H of formations for the reactants. Okay, so in here, the delta H for combustion we know is equal, oh no, I'm sorry, this is what we're finding. We're given the delta H of formation of the soybean-based derivative here. So if we want to calculate the delta H of combustion, we're going to take the sum of the delta H of the products. So we're going to have the 20 CO2 gas and the 18 H2O liquid as the products. So we'll take 20 times the delta H of formation of the CO2 gas, which is negative 393.5 kilojoules per mole. And we'll go ahead and add 18 for the water and multiply that by the delta H of formation of H2O liquid, which is negative 286 kilojoules per mole. So that's it for the products. And now we'll subtract the reactants. So we have 1 times the delta H of formation of this soybean-based biodiesel, and that's given in the problem as negative 770 kilojoules per mole. Okay, and then we'll go ahead and add 29 times the delta H of formation for O2 gas, which is 0 because it's in its standard elemental state. Okay, so let's go ahead and run out the math here. And we'll get that the delta H for the combustion reaction is negative 12,248. And this is going to be in kilojoules per mole. And the question requests that we report the answer in kilojoules per gram. So in order to do that, what we're going to do is take the negative 12,248 kilojoules per mole, and we're going to multiply by the molar mass. And we're going to do that with moles on top so that we get kilojoules per gram at the end. So we'll say that 1 mole of the soybean-based derivative is, and if you go ahead and add up the individual species, so we had 20 carbon atoms, those are about 12 grams per mole. We had, let's see, 36 hydrogens, those are about 1 gram per mole, and we had 2 oxygens that are about 16 grams per mole. So if you go ahead and add all that up, you'll get that the molar mass of this thing is about 308 grams. And so when we multiply this out, moles will cancel, and we'll get the answer in kilojoules per gram. And that's going to say, it's going to give us that delta H of combustion is about negative 39.7. And this is now in kilojoules per gram. Okay, so let's look at part C here. So in part C, we're looking at the delta H of combustion values for biodiesel, and we're comparing that with petroleum-derived diesel. So bio is about negative 37 kilojoules per gram of material, and petroleum is about negative 42. So if we want to look at these and compare them, we can compare them 2 different ways, per unit mass and per unit volume. So let's first do this by unit mass. So we'll do this by taking the ratio of biodiesel to petro. So what is negative 37 kilojoules per gram divided by negative 42 kilojoules per gram? So this is going to give us about 0.88, which is 88%. So that means that the energy efficiency, the energy content per unit mass of the biodiesel is about 88% of the petro. Or it's about 12% less efficient for the biodiesel. And this is by mass. So now let's look at this by volume. So if we look, let's convert to kilojoules per centimeter cubed, and that will help us see what values we're dealing with. So let's start with the bio. So we have negative 37 kilojoules per gram, and we'll multiply that by the density. And given in the problem, 0.88 grams per centimeter cubed. For 1 centimeter cubed. And so that's going to give us negative 32.56 kilojoules per centimeter cubed. So that's the energy content per unit volume. And now we'll do the same thing with the petroleum-based. So negative 42 kilojoules per gram. And then we'll multiply this by its energy density, or sorry, regular density, 0.83. And this is grams per 1 cubic centimeter. Okay, so now we'll get the energy content per unit volume for the petroleum, and that's negative 34.86. And this is in kilojoules per centimeter cubed. Okay, so now we'll go ahead and we'll take the ratio of these two things. So negative 32.56 divided by negative 34.86. That's going to give us about 0.93. So the bio-based is about 93% as efficient as the petroleum, or you could say about 7% less efficient for the biodiesel. And that's on a per volume basis. Okay, so now in part D, we're going to be looking at petroleum-based diesel and the sulfur content versus the sulfur content of biodiesel. So sulfur, there's a little bit more sulfur. So let's write this out in D. So in petro-based, about 0.2% sulfur. And just get a little bit more room here. The bio is much less. So 0.0001% sulfur. So the advantage of this is the biodiesel having less sulfur content means that there are less sulfur containing species given off during combustion. And this is important because sulfur containing species are greenhouse gases, and that makes biodiesel much more environmentally friendly. So I'll finish this off. Given off during combustion, much more friendly for the earth, much better byproducts.